Okay, so our next gas law has to do with this Frenchman, Charles, and his love of hot air balloons. So what does hot air balloons have anything to do with gas laws? Well, a hot air balloon is basically created because you take a container of gas and you heat it up, right? You release gas, you burn this gas, and you create this hot air, and hot air expands. So we know that, and as it expands, it gets less dense, and therefore it's going to float. So that's how a hot air balloon is going to work. Now, why does that work? Well, because we have this relationship between volume and temperature. So what does temperature actually do to gas particles? Well, when you increase the temperature of gas particles, so if you increase temp, the particles move faster. And if the particles are moving faster, that means they're going to spread out. And spreading out is basically the definition of taking more volume. So Charles' law is really very simplistic if you think about it from a common sense perspective. If you increase temperature, you will increase in volume. So these have a direct relationship, right? Boyle's was inverse, Charles is direct. So what does that look like graphically? Well, graphically that is going to look like a straight line going right out. As long as you are looking at volume on the y and 1 over temperature, right? Do note that that says, oops, no, not 1 over temperature. It's just temperature. My bad. Don't want to give you incorrect information. So we have volume and temperature on the x-axis. Now, there is an important thing to note here. That temperature must be in Kelvin. What happens if it's not in Kelvin? Well, that graph doesn't look quite the same way if it's not in Kelvin. So the graph would look a little different if you were not in Kelvin. So if you were in, say, degrees Celsius, the graph is going to look like this instead. Same shape, but why is it going on here instead of down here? Well, it's because these two temperatures are in the difference between Celsius and K. Because remember, at this temperature, 0 degrees K, all right, equals absolute zero, which means you have no motion. Remember? So Charles basically predicted absolute zero before Kelvin had ever thought of it, and he did it through this graphical representation. So he knew that his graph, this black graph, didn't quite make sense. So when Kelvin came around with that new temperature scale, everything that Charles did made a lot more sense. Okay, so we've got our let's reload here. So we've got our little simulation. And this is looking at temperature and volume again. So our pressure is staying the same. Our number of particles are staying the same, but our volume is changing with the temperature. So at these higher temperatures, all the way up to like 450, you get the largest volume. At the lowest temperatures, on here down to 250, you get the smallest volumes. So again, that is a direct relationship between those two values. So what do we mean here when we need to look at Charles' law calculations? So this is our formula, and please note that is a fraction bar. So you're going to write it typically as V1 over T1 equals V2 over T2. So yes, they are in a direct relationship, but the direct relationship means that when volume and temperature are on the same side, they're actually in a fraction form. So you have temperature in the denominator, and you're always going to see in all these other formulas that I'm going to show you in the next couple of videos, temperature in the denominator. So Just like the Boyle's Law, the 1 and the 2 just represent two different states. So 1 represents the initial temperature and volume, and 2 represents the new or changed temperature and volume. And our volumes, you're still primarily going to see milliliters or liters, but your temperatures are always going to be Kelvin. Now, they are normally going to give you Celsius, and you will have to convert it to Kelvin. We've done this last year, and remember the formula is Kelvin equals degrees Celsius plus the magic number of 273. And while that is on the AP formula sheet, that just needs to be automatic for you. All right, you should never have to look that formula up. So, we've got 4 different variables. We have V1, we have V2, we have T1, and we have T2. And you need to be able to solve this formula for any one of those things. So I put V1 and V2 first because those are the easy ones. If I want to isolate V1, I need to clear out the T1 in the denominator. So I need to do the inverse operation. It's in the denominator. It is divided, right? Denominator means divide. So I need to do the opposite of that, which is multiply. So if I multiply both sides by T1, I get my V2 over T2, which was already there. But now I am also multiplying it by the T1. Likewise, for the V2, I would already have my V1 over T1, but I've got T2 in the denominator because it's dividing, so I need to multiply both sides by the T2, which puts it over here. Now for the T1 and the T2, isolating variables that are in denominators tend to be difficult for people. So what I want to do for you is just show you how you can cross multiply from this format, and then you can make the formula look like V1 T2 equals V2 T1. Now that looks a little bit more like Boyle's Law, where they're next to each other, they're multiplied. So if I want T1, then I need to get rid of V2, which is multiplied, so I'm going to divide it. So that means I take my V1 and T2, and the thing I needed to get rid of was the V2, which is divided by. Likewise, if I need to isolate T2, I have to get rid of V1. So I would have my V2 T1, and I would need to put it over the V1. So I'm telling you now, it's these two temperature ones. When you're asked for those, that's where people mess up. So pay attention, make sure you get that formula down correctly, and use the right one. Okay, practice problem time. So back with Zippy. When Zippy arrives at the football game, he forgets the balloon in the car. The balloon's volume at this point is 5.5 liters. Assign that as V1 because it's the first thing I come across. And the temperature is 2.0 degrees Celsius. That's a temperature, so that's a T1. While in the car, the hot sun increases the temperature of the balloon to 26.5 degrees Celsius. New condition, so that's a T2. Assuming the pressure remains constant, those are important words, what is the balloon's new volume? So the question is asking me for V2. So what happened to my temperature in this problem? Well, I started at 2.0 and I went up to 26.5. So my temperature increased. So volume should also increase because this is direct relationship. So it's important again to think through that relationship first. Then when you do the problem, you're verifying your answer, okay? So next thing I need to do, I need to deal with these temperatures because these are in Celsius and I can't have them in Celsius. I need them to be in Kelvin. So T1 is 2.0 plus 273, which means it's 275 Kelvin. Now, why did I not write 0.0? Well, I didn't write 0.0 because this doesn't have a decimal point. This is addition. I take it to the least number of decimal places. So for my T2, that is 26.5 plus 273. And that is going to give me 299.5 Kelvin, except I need to drop that off, and that would actually be 300 point Kelvin. Okay, so I've got my formula for V2. V2 is equal to, what did I have on the other side? Let's see here, my V2, it's T1 times, it's T2 times V1 over T1. There we go. So I've got my two things in the numerator. So my T2, which is 300, times my V1, which is 5.5. And I am dividing all of that by my T1, which is 275. So think right now, how many sig figs should I have? Well, this has 1, 2, 3, this has 1, 2, 3, but this only has 1, 2. So I should have 2 sig figs in my final answer. So in my calculator, I'm going to open a parentheses, 300 times 5.5, close the parentheses, then do my divide by 275, hit an equal, and to two significant figures, my answer is going to be 6.0 liters. And I need to verify, did my temperature or my volume actually increase like I predicted? And yes, it did. It went from 5.5 to 6.0. So I think I set up the problem correctly.